All right, welcome back again. So today we're going to be doing section 15.3, continuing our journey through multiple integration. We're going to stick with integrals or double integrals for now. And today we're going to talk about integrating over polar regions. So let me get the slides up and let's get going. All right, this one is actually another relatively short section. And if you followed what I was talking about in lecture 15.1 with the mechanics of the integral, then this should be very quick to pick up on. But there are some really important ideas here in the development of this mechanism, the mechanics of the integral, because we're going to see it over and over and over again in this section. So it is important to make sense of it so that you don't get too lost down the line, right? So there's only three subsections: development of the integral mechanics. Then we're going to do some double integrals in polar coordinates. And then we'll generalize it to integrating over polar regions between two curves, two polar curves. So let's start with this. Back in Calc 2, you explore how sometimes it's easier to describe a region if it's given in polar coordinates, right? Sometimes regions are just more nicely described if they are radial in nature. Yeah, especially if they're radial in nature as opposed to rectangular. So now what we're going to do is we're going to see how to integrate over these regions that are described this way. What do we need to do? Well, we need to adapt the mechanics of our integral, and we need to basically tell it how to process these functions that are given in polar coordinates instead of rectangular coordinates. Um, well, the way that we start this is we use the isomorphism equations between the polar coordinate system and the Cartesian coordinate system. So just like a flashback from trigonometry or Calc 1 or pre-calc or Calc 2 or something. If we want to convert from polar to Cartesian, we have these relationships here, right? So we're going to use these things. Or from Cartesian to polar, you would also need tangent to get back an angle, but we won't go through all that. Anyway, x is r cosine theta, y is r sine theta, and r squared is equal to x squared plus y squared. That's just a Pythagorean identity. So we're going to need those. And if you remember from when we developed the integral mechanics for the double integral, we basically partitioned our rectangle into a bunch of sub-rectangles, right? We're going to do the same thing now, but now we're going to partition it into polar rectangles or polar subrectangles. So what is a polar rectangle? A polar rectangle basically looks like this, and it's a rectangle of the form given here, where essentially you are talking about a region that is between two rays, and then also between two corresponding radii. So these are the two rays. You like integrate between those two angles, but then we're also going to integrate from this radius to this radius. So this is what we call a polar rectangle, all right? Now, just like we saw in 15.1, if we want to compute an integral over such a region, we're going to divide the interval a comma b into m equal width subintervals called delta r. So this is the interval from a to b, basically right there. All right, and we're going to cut it up into some subintervals, and then we're also going to divide our angle interval into subintervals, right? So here's this to here. We're going to cut it up into some subintervals like that. We're also going to cut this into some subintervals like that. And then what is the result? You get a bunch of polar subrectangles. That's what all these things are, polar subrectangles, right? Here they are. So r sub I sub j, I can zoom in a little bit just to show you. And the process is going to be identical. It'll feel very, very familiar. Once we have these polar subrectangles defined, we can pick a sample point. In this case, wait, what do I have? R sub I star. Yeah. In this case, we're just going to pick the quote center of these polar subrectangles by taking the average of the radii and then the average of the angles, the rays, right here. And that'll give us this little center point, r sub I star, comma, theta sub j star. Now, our Cartesian coordinates are x and y. So if we wanted to write the location of this point, the center point, in terms of polar coordinates, it's going to be this. So x is going to be r cosine theta, and y is going to be r sine theta. So that's how we're going from the Cartesian representation of the point to the polar representation of the point. All right? Now we got to find the area. So we found a way to talk about these actual points, but now we need to be able to find the area of each one of these polar subrectangles. So how do we do that? Well, you might recall the area of a circular sector, maybe from trigonometry or pre-calculus or something. So the area of a circular sector that has radius r swept out by an angle theta is really just taking the portion of the total area of the circle represented by your angle theta. This is how I always remember this formula. Pi r squared is the area of the whole circle. Theta over 2 pi is the fraction of the circle that we're going to take, right? And then through some nice simplification, pi's cancel, you get 1/2 r squared theta. So this is like the simplified version of that formula. Now, if we have two circular sectors that have a central angle delta theta, so you can just think of it as like, one of these right here, but here's one circular sector right here, this big one, and then here's another one, this smaller one. We're going to take the difference of those two sectors, and the difference will give us the area of that little polar rectangle. So that's exactly what we're going to do. We'll call that the change in area, right? So this is going to be the area of the bigger circular sector minus the area of the smaller circular sector. And then when you basically do a little bit of manipulation, do a little bit of massage, you can rewrite this delta A sub I like so. So this is actually a difference of squares. So you get that. But remember that r sub I minus r sub I minus 1, that's delta r. That's the change in radius, right? And then this right here, this is quite literally the midpoint. It's the quote midpoint of that polar rectangle, right? So it's r sub I star. There it is. Or maybe I should say the midpoint of that line segment between the two radii. There you go. So how are we computing the area of one of these? It's like this. That's what the area is. Let's get a little bit of intuition for this. So intuitively, what this area is, the area of that polar subrectangle, it's broken into pieces. So if you look at this first piece right here, let me get a blue color here. There we go. Oh, wait, I think I might have copied this down wrong. Hold on. Give me 1 second. That's delta r sub I. So the length of, yeah, no, I guess I left it. No, okay, this is right. Hold on a sec. Let me do this. Circle this and this. Yeah. Okay. Maybe I'll go back to the picture too for a minute here. So if you look at this product right here, r sub I star times delta theta, that's the length of the arc that passes through that, wait, through that, which way am I going? Midpoint? Let me just show you here. It's basically the length of this right here. It's the length of that blue line that I just drew, where it passes right through that midpoint. That's the length of that right there. And then what we're going to do is we're going to multiply it. Oops, hey, there you go. And then we're going to multiply it by delta r. That's the next piece right here, delta r. So delta r is the side length of that rectangle. So let me go back to the picture one more time. Delta r is this. So what we're doing to get the area of that rectangle is it's kind of like we're taking this length that you see right here, and we're copying it a bunch of times to the left. So it's like we're going like this. It's like we're going just like that. That's how we're getting the area. How do we do that? We basically take this length and then we scan it that way, and then we add up all the results. So that's really what's happening when you see this, this formula right here for delta A, or delta A sub I. Okay, I mentioned it here, but this is actually an instance of the first theorem of Papus. So hopefully you talked about this when you went through the section on volumes of rotations, or volumes of solids of revolutions. So you can use a theorem of Pappus to find the volume of a solid of revolution really easily if you know the path that the centroid takes and you know the area that you're kind of moving. That's exactly what's happening here. Incidentally, this is why we call it a polar rectangle, because it is kind of like length times width. And that would give you the area of a rectangle normally. But in this case, there's an additional scaling factor to account for um, that curvature, basically. That's really what it's doing. So now we have all the pieces. So this is also going to sound very familiar. The volume of one of these polar columns, so imagine a column above each one of these subrectangles, right? Now we can find the actual volume. So it's going to be the height of our function at that sample point times delta A sub I. But remember, we're going to convert these into polar. And we just found that delta A sub I is actually this. So our formula becomes this for the volume of one of those polar columns, which makes sense, right? Height of the function times the area of the base gives us the volume. Then we're going to add up all of these volumes, and that will give us an approximation of the actual volume itself. So we add them all up. That gives us an approximation. And then this is what our formula looks like. Maybe now you can guess what's going to happen next. You take the limit as m and n go to infinity, and we have, voila, change to polar coordinates in a double integral. So this is how you do it. Like if you want to take a double integral that's written in terms of Cartesian coordinates and you want to convert it into an integral that's written in terms of polar coordinates, this is what you do. All right, so here's the formula. Again, change x and y to r cosine theta, r sine theta, respectively. There's this r here that we got from that scaling factor, and then there's dr d theta. Here, r goes from a to b, and theta goes from alpha to beta. Cool stuff, huh? I think it's cool. Okay, so a couple of things. Important note, do not forget the extra factor of r. There's an extra factor of r in there. That's why we needed it. And when we found the area of that polar rectangle, that r popped out, so we must have it. This is the area. This is the infinitesimal area of one of those polar rectangles, right? If you don't have the r, you do not have a polar rectangle anymore. You've got like a Cartesian rectangle that's not really working for what you're doing. You're not going to have equality here, right? So one thing I want you to do is I want you to note carefully the structure that you see here of this, you might call it a two form or an area form. And if you want to go down a very deep rabbit hole, this link will lead you to, frankly, like the wedge product and exterior algebras and how you can generalize this idea on manifolds. You don't have to, but it's there. This is the area of the infinitesimal polar rectangle. So that's why we're getting function value times area. That gives us volume, and then you add them all up. So there's still that intuition throughout this whole process. Now, this factor of r, that's actually just an artifact from the more general construction of a change of variable. So you've learned change of variable in integrals already. You saw it with the substitution rule. You saw it with the inverse substitution rule. You saw it with trigonometric substitution. And we're going to explore it in generality in section 15.9. So that's the section where it's like, okay, well, what if we want to take our region and transform it more generally into a different region? What happens to this this area form, or what happens to this structure right here? That's what 15.9 is all about, doing this in general. But you have been doing it before, because remember, we're preserving the value of the integral. Wait, do I say that? Yeah, I say that right here. Yeah, we're changing the parameterization of the function, and we're changing the parameterization of the infinitesimal rectangle, but the value of the integral is preserved. This is actually one of the reasons that I always harp on my students in Calc 1 about changing the bounds of integration when you do like a U substitution, right? Because you're changing the whole setup, but you're preserving the value of the integral. That's the important part. We want to preserve the value of the integral even if we change the representation of the stuff, right? Now, in practice, this conversion really should be used to make your integration easier. It should make your life easier. So when do you employ this conversion? You employ it when the region of integration is more simply described using polar coordinates. That's pretty much it, right? So that's like the moral of the story for this section. Like, would it be easier to describe my region in terms of polar coordinates? Yeah, I think so. Okay, so then write it in terms of polar coordinates. That's what you want to do. All right, let's try it, okay? Um, I want you to try to do this one on your own, and then we will do it together. So evaluate this integral here, where R is the region in the upper half plane bounded by these two circles. Okay, so I want you to think about it first. All right, now say something out loud. Give your brain that feedback to help you organize your thoughts. Maybe what would you try first? Okay, now try to work it out on your own using polar coordinates, using integration, and then we'll do it together. I want to emphasize, do not use a basic geometric argument for this. Use the integral, and we'll verify it using a geometric argument. Okay, here we go. So one thing that can help, I always recommend this if you can, is to try to make a sketch of the region over which you're integrating. So this is what the region looks like. Um, it's in the upper half plane, right? And it's bounded between these two circles. So that orange region, this is where we're going to integrate. That's what it looks like. Uh, if we wanted to write it in terms of Cartesian coordinates, this is the region that we want to integrate over. But as you can see, it's just ripe for polar coordinates. It's not that we couldn't integrate this rectangularly, right? You could integrate it by going like this, right? And then like this. But that seems like it would be more difficult than if we just represented this region in a way that's more natural to its structure, in particular in a polar way, right? So how do we write this in terms of polar coordinates? It's really much more simple, right? Here, the radius goes between 1 and 2. And our angle theta goes between 0 and pi. So what we're going to do is, rather than telling our integral to scan vertically, and then scan horizontally, we're going to tell it to scan radially first, and then around this angle like so, and then rotationally, because that's what it does. It's a scanning machine, right? It scans. We just got to tell it how to scan. That's the idea. Okay, now that we've got the conversion, this is what it becomes. So this is the integral we started with, and we reparameterized the region in terms of polar coordinates, and we changed our variables from x and y to variables that involve r and theta. There we go. And that's just using those isomorphism equations. X equals r cosine theta, y equals r sine theta. And remember, we're changing the area form. So dA now becomes r dr d theta. Remember, you need that extra factor of r in there to make it valid. And then this is what our integral becomes. Here's 3x, here's 3y squared, and here's dA. Boom. Now, good old iterated integration. Go for it. So the rest of it should be pretty straightforward at this point, right? So we get this function here. Sorry, I should say this function here. I distributed r to both terms. Now I'm going to integrate with respect to r. Good old FTC2. Gotta love it, right? Good old FTC2. Now we're left with a function in terms of theta only. And well, at this point, you can integrate it however you know. So here we're actually going to use the power reducing formula. That is one of the 6 formulas that I say you have to memorize. So make sure you have memorized those 6 trig identities. This is one that you're going to use a lot in calculus. So make sure to memorize the power reducing identities. Then apply FTC2 once again to theta, or to this function in terms of theta. Simplify, and you get 15 pi over 2. Boom. There we go. Okay, now this one is actually one that we could pretty easily verify geometrically. I'm going to go back to the region. So let me throw this region back up. Maybe this will motivate an example that comes after the next one, but we can verify that we're correct, right? Because if we wanted to find the area, or what do I say? The what do I want to say? Not never mind, never mind. You could find the area of this region just by basically finding the area of the two circles, cutting them in half and subtracting, right? But don't forget, we're going to integrate over this as well. Okay. Where was I? Right there. This one. Oh, shoot. Okay, pretend you can't see this. This was the next example. Okay, so next example, pretend that you cannot see any of this. It's hidden. No looking. Forgot to put a pause in there. Okay. So here's another one where I want you to try to do this one on your own. Where is it? There. Okay, think about it for a minute. You see nothing. All right, now say something out loud about how you would start. Not by looking at the solution. And then try to work out the solution, and we'll do it together in just a minute. Okay, here we go. All right, so we want to find the volume of the solid bounded by the xy plane. Oops, let me erase this stuff. There we go. By the xy plane and the paraboloid given by this function here. Now, yeah, so z equals 0 on the xy plane. So that means that our planar region of integration is given by this right here. Rewriting it, we see this is just the unit disk centered at the origin. So that's our region of integration, the unit disk right here. Now, because it's the unit disk, ripe for polar coordinates, right? We can write it in terms of Cartesian coordinates, but in polar coordinates, it's even easier. R goes between 0 and 1. Theta goes between 0 and 2 pi. There's no squares. There's no squares or anything like that. Literally just r's and thetas. Now, we have to also convert our surface, right? We have to convert this function to be in terms of r's and thetas. But maybe you can see, remember, x squared plus y squared is equal to r squared. So we can change x squared plus y squared to r squared. And so this expression becomes r squared, and then the whole thing becomes 1 minus r squared. So now we've got everything. We converted z to be in terms of r, and we've got our bounds in terms of r and theta. Now we can do our integration. Boom. So what is the volume of this region? This is the integral we wanted to calculate. We iterated the integral like so. Here's z, and dA is now r dr d theta. And now it's just super simple integration. Hopefully you feel a breath of relief when you see something like this, because it's just like, oh, power rule twice, yay. So r minus r cubed, ftc2 on r. We're left with this, ftc2 on that function of theta, and we get pi over 2. And that's it. Not too bad. Okay, let's make things a little bit more interesting here. So sure, I mean, there are some nice regions like disks and annuli and like half annuli and things like that. But we want to generalize this to general polar curves. So we want to be able to integrate regions that look like this, where this curve is a polar function, or I should say a curve defined by a function of, polar coordinates, theta. And then same with this one too, right? So let's start with a region that looks like this. So consider this region D. We can describe it like so. Theta goes between alpha and beta, and our R goes between these two curves which depend on theta. Just like a good old polar curve from back in Calc 2. So this is going to behave exactly like we saw back in the last section, right? 15.2, where we were integrating over general regions. The only difference now is that our regions are described in terms of polar coordinates. Here it is. Yeah, so we integrate our function between these two polar curves, and then we integrate theta between alpha and beta. And that's how we do it. Pretty cool, huh? Don't forget to change x and y to r cosine theta and r sine of theta, and don't forget the extra factor of r, because we're converting everything to polar. Okay, here we go. This one might be a little bit of a challenge. But I'll leave it to you to think about for a minute at least, all right? So find the volume of the solid that lies under this paraboloid, above the xy plane, and inside this cylinder. So just think about this one for a minute. And then I want you to say something out loud about what you can see in your head. Kind of helps to try to visualize this kind of a thing. Right. And now if you would like to, try to work it out on your own, but we're going to have to be a little bit clever. We're going to have to change at least one thing before we do our integration. Right. Now let's do it together. So the paraboloid has the vertex 0, 0, 0, which lies right on the xy plane. So when you see this, I'm hoping you can kind of visualize what it looks like. It's basically a circular paraboloid that opens up, and its vertex is right at the origin. Circular because there's no scalars here, right? So we're going to integrate, so this thing right here, and we're going to integrate above the xy plane, and we've got to integrate inside the cylinder. So this is the tricky part here, inside the cylinder. And the fact that we have this linear term, this 2x term, what that means is that our cylinder is going to be shifted away from the origin. That's what this extra linear term means. So how do you find that? You have to complete the square. So if you complete the square in x, then what you can do is you can rewrite this circle or this disk like so. Well, this circle, I should say, this circle. So it's a circle that's been shifted away from the origin 1 unit in the positive x direction. And now you see, now you really got to think about what this is. So we're integrating above this disk, but below this paraboloid, right? Let me show the picture and I'll come back for a minute. This is the picture. So here's the paraboloid, here's the cylinder, and what we're doing is we're actually finding the volume of the region that is underneath the paraboloid, but inside the cylinder. So it's this right here. I like these kinds of problems and even like the volume problems from Calc 1 and Calc 2 because you ever like look around at different, I don't know, maybe architectural constructs and you're like, what's the volume of that thing if it's such a weird irregular shape? We can do that. Like we can find out the volumes of these things as long as we have functions that describe these surfaces. And then we can use the integral to compute the volume. You might need to know that kind of stuff. Like if you wanted to design a building that has a really, you know, intriguing, like, I don't know, like roof structure or like ceiling structure, and you need to know the volume of that room. Like how much, like how are you going to cool the room without knowing the volume of air that you need to cool down, right? Because once you know the volume of air that you need to cool down, that will tell you how many air conditioning units you're going to need. So there's all of this math that goes into these things. It's kind of behind the scenes. That's why I like multivariable calculus. It lets you get at a lot of these really interesting ideas that you've probably been pondering in your own head for a while. Okay, so looking at this really does feel like it would be easier to integrate in terms of polar coordinates because we're integrating over a disk and we're integrating underneath something that has this radial behavior. So polar coordinates seem like a good idea. And this is what it looks like, representing it in polar coordinates. All right, so let me see. This is our region, right? So, okay, let me try to explain the region. The region that we're integrating over is this disk, right? So it's basically the unit disk that would be here, except now it's been moved over by 1 unit. Okay, so yeah. So what you really have to think about is how would I describe this disk in terms of polar coordinates? And that's this right here. So this is something that you might have to dig up out of your memory if you took Calc 2 a while ago, but this is the equation of a circle with radius 2. Oh, I'm sorry, that's the diameter. The diameter is 2, but it's been like shifted in the x direction. So you might have to dust off some old knowledge about polar curves and things like that. All right. And then we're going to integrate I'm sorry, and then it goes from negative pi over 2 to pi over 2. It's kind of like going from like here to here. Might be a little hard to see, but okay. Now we kind of have everything we need. The good news is that our paraboloid is again just ripe for polar coordinates because you've got this x squared y squared relationship. X squared plus y squared is r squared. There it is. And r is going to go from 0 to 2 cosine theta, and theta is going to go from negative pi over 2 to pi over 2. Boom, that's it. There's our area form right there. r d theta, and now the rest is good old integration. Here we go. R cubed is pretty easy to anti-differentiate, ftc2 right here. Then you get a function that's only in terms of theta, and now you're back into good old integration techniques. How would you integrate cosine to the fourth? If you're lucky, you've been talking about it since pre-calculus, but you're going to use power reducing identities a couple of times. Actually, this is a question that I know. I think I even put on my tests in Calc 2. So you should definitely know how to do this one. Power reducing formula again after you FOIL everything out. Then again, you've only got stuff in terms of theta, FTC2, simplify, massage, combine like terms, and you get 3 pi over 2. Nice, cool stuff. All right, and on that note, it's time to play. So this one is another one that's pretty short. The takeaway you should really have from this section is that formula for integrating in polar coordinates. Let me flash it back on the screen real quick. This one. This is the one. That's what you want. That's the one you want to know. So you should memorize this, but again, you shouldn't really need to memorize it. Just remember how you're converting everything into polar coordinates, and you should be good. All right. But that's about all I had to say. So I guess I'll end it about here. Thank you all again for watching and listening. If you've got questions, let me know. I'm excited to work with you on this, and I'll see you next time. Take care.